I'm going to start by the anatomy of the cornea. The cornea is the transparent part of the outer coat. It is continuous with the sclera at the limbus. Through the cornea, we can see the iris and the pupil. So here, the cornea, and this is the limbus. And here we can see the sclera covered by the transparent conjunctiva. This is the diameter of the cornea. And
so now, as you can see here, vertically the cornea is around 11 millimeters and horizontally it is around 12 millimeters. So the vertical cornea is smaller or lesser because it is covered more by the sclera, or there is a scleral conversion of the superior part of the cornea, because of which the vertical diameter of the cornea is lesser than the horizontal.
the cornea has a thickness of 0.5 millimeter in the center and 1 millimeter toward the limbus. Light coming from external world will pass through the cornea, then through the lens to get focus on the retina. The cornea is a very strong plus lens of a power plus 42, while the crystalline lens has a power of only 18. So the cornea make up 2/3 of the total optical power of the eye. The central part of the cornea has a radius of curvature of 7.8.
So radius of curvature means it is the curvature formed at one particular point, and that particular point, the curvature is taken as an imaginary circle, just like the yellow circle you are seeing here for the central part of the cornea. In that sense, the curvature is actually varying at different parts of the cornea. As you move towards the periphery, you seem to be getting bigger circles because the radius of curvature tends to make it more flatter, or the radius of curvature of the circle will be higher. So cornea is not part of a complete circle. It has different radius of curvatures at different points. For example, the central area is having more curvature, because of which it involves a smaller circle, whereas with regard to the curvatures of the periphery of the cornea, you can form bigger circles, which is because the cornea is flatter towards the periphery. So now, what is the role of cornea? You know that it functions as a refractive media. Its transparency is actually because of the regularity, smoothness and vascularity, because of which the refraction is possible. And it is also a very good physical barrier which prevents any trauma or infections, and it helps to maintain the integrity of the eyeball. As we have already seen, the different textbooks give different values. We can always round up the vertical diameter to 11 millimeters and the horizontal to 12 millimeters. The radius of curvature, as we have already seen, is of the anterior part is 7.8 and the posterior part is 6.5. So what I would like to stress here is cornea is not a single line. So you cannot imagine the curvature to be the same. It has an anterior surface. It has a posterior surface. So the anterior curvature is definitely flatter and the posterior curvature is more smaller. So compared to the outer cornea, the inner corneal surface is more curved, or it is smaller. Also, with regard to the thickness, you should know that as the cornea extends to the periphery, the thickness is increasing. So if it is 0.5 millimeters here, you should know that it is the double, that is around 1 millimeter thick at its periphery. It's important to know the refractive index of the cornea, and it is 1.37. So the cornea is not it is a brilliant optical structure. Coming to the histological section of the cornea, we should know that it has an epithelium, a stroma, and the endothelium. So this part corresponds to the epithelium. This segment is belonging to the stroma, and this tiny layer here represents the endothelium. In between, you have two layers, that is the Bowman's layer and the Descemet's layer.
Okay.
So how do you remember this in order? There is always a confusion existing whether between Bowman's layer and the Descemet's layer, which is on the anterior part. So it's easy to remember the mnemonic as A, B, C, D and E. So it will be A, B, C, D, E. A stands for epithelium, B for Bowman's layer, C for stroma, D for Descemet, E for endothelium. To understand the epithelium, you should know that there are superficial flatter epithelial cells which are called as the wing cells, and the lower layers are columnar epithelial cells. It is a stratified layer formed of 5 to 6 layers with a thickness of 50 microns. It is not millimeters. Now, as you go towards the limbus, that means as you go towards the periphery of the cornea, the number of stratified layers increases from 5 layers to 10 layers. That is, this number of layers in the epithelium increases as you move towards the periphery, from 5 layers to 10 layers. Now these wing cells are arranged in this way. So these two cells are held together by what are called as desmosomes, which forms a very tight barrier preventing penetration of water. Because if water happens to penetrate through the epithelium into the stroma, this can result in stromal edema, which will affect the vision. So these desmosomes act as a very strong tight barrier connecting adjacent epithelial cells together. Now, with regard to the lower basal lamina, which is the lowermost layer of the epithelium, these cells of the higher areas are connected strongly by what are called as hemidesmosomes. So between cells you call it desmosomes. With the lower basal lamina you call it as hemidesmosomes. Now the limbal basal layer causes superficial and centripetal displacement of older cells within newer ones. So when you have the corneal epithelium in this way, you know there are a lot of epithelial cells here. If somebody gets damaged because of a trauma, it is the limbus at both sides which has limbal basal stem cells, which regenerates new epitheliums to grow and come to the center from all around the cornea. Now these limbal basal stem cells has an immediate response to disruption in the integrity of the epithelium, and it is actually the amoeboid movements of these epithelial cells which helps in the regeneration. So it first moves towards the center and then it replaces the columnar epithelial cells first and then forms the superficial wing cells. The central part of the epithelial cells are devoid of melanocytes and immunocompetent cells like MHC class 2, dendritic cells and Langerhans cells, which is a statement in SIU question. Now the epithelium is actually continuing as conjunctiva after the limbus. Next is the Bowman's membrane. You should know that it is an acellular membrane and it has about 8 to 12, roughly it is 10 microns. Microns allada 50 millimeters alla. Microns are millimeters alla. The thickness is around 10 microns. The collagen that forms the Bowman's membrane is 1, 3, 5 and 6. We already discussed that the epithelium is changing into the conjunctiva after the limbus. Bowman's membrane will stop at the limbus. With regard to the stroma, we should know that the stroma is remarkably transparent. The transparency has astonished various scientists. There are a lot of theories being suggested with respect to the transparency maintained by the stroma. Stroma is actually made of a lot of thick, flattened, collagenous lamellae, and the thickness of the stroma is around 500 microns. Now these lamellae are actually arranged in a brilliantly parallel manner, and it is continuing with the sclera at the limbus. And it is the stroma that makes up 90% of the corneal thickness. The only cells that you happen to be seeing in the stroma are called as keratocytes. The transparency again is actually due to the regular spacing of the collagen fibers, and there is some coordination of these collagen fibers with respect to mucopolysaccharides, which are seen in the corneal stroma in the name of glycosaminoglycans and proteoglycans, which are called as keratin sulfate and chondroitin sulfates. So glycosaminoglycans and the keratin sulfates are mucopolysaccharides, which are seen in the corneal stroma. The next layer, as you can see, is the Descemet's membrane. Descemet's membrane is periodic acid Schiff staining layer of the cornea, which is around again 10 microns in thickness. You remember the Bowman's membrane was 10 microns. Similarly, the Descemet's is also of the same thickness. It has hexagonal arrangement of its tissue. Now, in fact, after the Descemet's, you see the endothelium, which is also hexagonally arranged, which are hexagonal cells in fact. So some also call the Descemet's membrane as the basement membrane of endothelium. It has two layers. The anterior is the banded and the posterior is non-banded, which is closer to the endothelium. Is non-banded. The anterior one is banded. Now this Descemet's membrane are rich in glycoprotein laminin with type 4 collagen, and this is a very important statement to know that Descemet's membrane are terminating as the Schwalbe's line, which is a structure you see in the angle of anterior chamber. Now this is continuing after the Schwalbe's line in the trabecular meshwork. At the periphery, we see Hessel-Henle bodies in the Descemet's membrane due to aging, which is actually protruded thickenings of the Descemet's membrane. It's important to know that it is seen in the periphery of the cornea, not at the center. Now, if the Descemet's membrane is damaged for some reason, it curls around itself. In the anterior chamber. Now, the next layer or the innermost layer of the cornea is the endothelium. The main role of the endothelium is it has a pump which operates and drives out all the edema that gets collected in the corneal stroma. There is a pump which works and drives out all the edema or stromal or the collagen productions or waste materials, and there is a pump operating for it with the help of endothelium that pumps out these things into the aqueous, which is the waste carrying channel that is replenished into newer aqueous cells. Now, the endothelial pump helps in maintaining the corneal hydration, and thereby the transparency of the stroma is well maintained. Now, this is endothelium is actually a single layer, unlike epithelium, which had 5 layers in the center and 10 layers at the periphery. Here endothelium is a single layer. And there are, in normal individuals, there are around 3,50,000 cells per cornea, or we can say that the density of endothelium is 3,500, which is normal, and as age progresses it decreases to 1,000. In very old individuals the density comes to 500. Now, the role of endothelium is, as I said, is to maintain the transparency of the cornea. But if for some reason the endothelium is getting damaged, it is having a very low regenerative capacity. That means if there is a trauma happening to the endothelium, that endothelium is not replaced with a new endothelium. Here the adjacent endothelium enlarges its size. So if these are the endothelium, we have to draw it hexagonally. And let's say if this endothelium is getting damaged, what happens is these endothelium enlarges its size and fills up the gap. Any damage to the endothelial cells and a density below 800 cells per millimeter square will cause edema of the stroma, because the pump will no longer be able to function efficiently and the stromal transparency will be lost. Now, the endothelium is actually continuing as the trabecular meshwork, which is again a structure we see in the ankle of anterior chamber.
The second layer is the Bowman's membrane. It is the most external layer of the stroma. If there is some injury to the Bowman's membrane, a permanent opacity will be there. Then comes the stroma, or the substantia propria, is formed of collagen fibers, specially arranged and compact, and in between the fibers we get the keratocytes, the corneal cells, and also we have a wandering white BCs. On the back of the cornea we have the Descemet's membrane and the endothelium. The endothelium of the cornea cannot regenerate.
Here you can see the limbal stem cells, which helps in the regeneration of the damaged epithelium, and this grows from the limbus into the epithelium during replenishing of the epithelium.
The cornea is transparent while the sclera is opaque. Why that? The cornea is transparent because it's formed of fibers of uniform size running parallel to the surface, and the fibers in one lamina is perpendicular to the fibers in the next lamina. Also, if this spatial arrangement is lost, as in case if we have haphazard arrangement of the fibers, then we get an opaque surface like the sclera, or if it occurs in the cornea, we get an opacity in the cornea. The second factor for transparency is that the water content of the cornea is only 70%. This is a relative dehydration of the cornea compared to the tear film and the aqueous humor. Both the tear film and the aqueous humor are almost 100% water. On the other hand, the cornea is only 70%. This is important to keep the cornea transparent, to keep the layers compact. To understand this, here an example of corneal edema. You notice the cornea is thickened in the center and it is bluish. This is the normal cornea, and this is an edematous hazy cornea. If you see here the view, all this part of the cornea, we get some haziness. On the other hand, everything is perfect here. To understand why the cornea becomes cloudy with the edema, let's have this example. This is the external atmosphere. This is the atmosphere of the Earth. As you can see here, this part looks bluish because rays coming from the sun, the blue end of the spectrum, is reflected reaching to the photo lens. So this part is blue. On the other hand, this part of the skies is white because the reflection includes the whole spectrum. This part has no color at all because there is no scatter of the rays from this zone. So to see anything, we need rays scatter into our eyes or into the camera. When the scatter is on the blue end of the spectrum, we see blue. When the scatter of the whole spectrum, we see white. When there is no scatter, we don't see anything. Now, in the eye, rays coming from outside pass through the cornea into the eye. Almost most of the rays get inside the eye, but we have some scatter here to reach to our eyes so we can see there is a cornea. The amount of rays coming here is minimal, but it includes the whole spectrum, so we see it grayish. If there is edema, then the blue end of the spectrum also will be scattered in great amounts. So the amount of light getting inside is less, and there will be haziness, so we cannot see through the cornea. So the cornea, to be transparent, we need the layers of the cornea to be compact to avoid the scatter back of the rays. The scatter back usually starts by affecting the short waves, but if the edema is more and more, the whole spectrum will be scattered back and the cornea will turn toward the white appearance. The cornea is protected anteriorly by the epithelium and posteriorly by the endothelium. Both act as a mechanical barrier, preventing water from getting inside. Also, the endothelium on the back surface all the time is doing what we call a sodium pump. It takes sodium from the stroma push it toward the anterior chamber, and water will follow. So that's why the cornea become of a less water content. If there is endothelial damage, the cornea will turn opaque. This is some examples of endothelial damage. Also, the cornea is transparent because of absence of opaque structures. A normal cornea has no vessels, blood is opaque, so if there is vascularization of the cornea, it will turn opaque. Also, the epithelium of the cornea is non-keratinized. Keratin is opaque. So if this is an example of a severe dry eye and the epithelium on the cornea and the conjunctiva is keratinized, and we get an opaque cornea. So these are the factors that will make the cornea transparent.
So now to repeat about the reasons for a transparent cornea. As you know, anatomically it is the arrangement of the stromal collagen, and the fiber size is uniform and they are arranged in a specialized manner. Even the distance between the arrangement of a lamellae is less than 1/10 of the wavelength of the light, because of which the transparency of the cornea is maintained. There is no scattering of light because of it. Next is, there are no opaque structures like blood vessels on the cornea. That means it is an avascular structure that helps in the maintenance of the corneal transparency. There are no keratinized epithelium, nor presence of any myelinated nerve fibers. So one is with regard to the arrangement of the lamellae. The next is with regard to the relationship to the wavelength of light. Third is the absence of opaque structures. So now coming to the nerve supply of the cornea, we should know that it is actually the fifth cranial nerve, giving away an ophthalmic division, that is giving off sensory fibers, and in the name of long ciliary nerve, LCN. Now initially these fibers are myelinated. When these fibers are at the limbus. Now the moment they get into the anterior corneal stroma, like at this point these fibers are myelinated. Now the moment they get into the anterior corneal stroma, it forms part of a sub-epithelial plexus under the corneal epithelium, and they get unmyelinated. And they are devoid of Schwann cells, and which may be the one they are getting. There are also hypothesis that these Schwann cells are getting invaginated by the keratocytes present in the stroma or the Bowman's membrane, and then it becomes part of an intraepithelial plexus. Now these nerve fibers are sensitive to pain and temperature as these nerves go deeper into the stroma. A revision again into the detail of the optics of the cornea. We should know that the horizontally it is around 12 and vertically it is 11. The refractive power of the cornea is 48 diopters, and it is actually the anterior is 48, and we know it is curved by 7 millimeters is the radius of curvature, and the other one is 6 millimeters of radius of curvature. And since the refractive power of anterior corneal surface is higher, it is giving a curvature of light by around 48 diopters actually. But you know that this is between air and the cornea, so the deflection is very high. Now from the posterior curvature, it actually goes into liquid, that is aqueous humor. So the refractive index difference between the cornea and liquid is lesser compared to the refractive index difference between the air and the cornea. So the light will bend more at the anterior surface but lesser at the posterior surface because of the refractive index differences. So when there is a curving of light by 48 diopters, because of this problem, that curvature is minused by 5 diopters and the net power of cornea is told to be around 43 diopters. And as I said earlier, central cornea is more curved, and as we go towards the periphery of the cornea, it gets flatter. So this tends to give you smaller circles, whereas this will give you larger circles. We are actually considering this point and making a circle out of that particular point based on its curvature. So as we move towards the periphery, we get to know that it gets more flatter. So the circle formed by it will have a radius of curvature that is larger. And also there is a difference between the anterior radius of curvature, which is around 7, and posterior is around 6. The refractive index, as we have already discussed, is 1.376. Little bit about the metabolism or the biochemistry of cornea. We should know the sources of oxygen, glucose and amino acids that supply the cornea. We should also know the role of glycolytic pathway and HMP shunt pathway in corneal metabolism or the corneal cell survival. The oxygen with regard to the epithelium is from the air. For the endothelium, it is derived from the aqueous. The mean total oxygen consumption is around 9.5 and the minimal oxygen tension is around 11 to 19. With respect to glucose, we should know that it is the energy source for the cornea, and for the epithelium it is again from the tear film, that is in the anterior part. So for the epithelium it is from the tear film that is there, and for the endothelium it is the aqueous again. The respiratory quotient is around 1. For the epithelium, the glucose consumption is 50 to 60 milligrams and 85% of the glucose is metabolized. The amino acid source is not very important, but if it is around 10 milligram per hour. Now glycolysis is the pathway by which the energy is being restored, and the byproducts are lactic acid. There is Embeden-Meyerow's pathway, you should be knowing. There is TCA cycle with regard to glycolytic pathway. Glucose consumption source is so, and it is around 100 milligrams per hour per centimeter square. There is also HMP shunt pathway. You should know its description in the form of ATP, NADPH and its uses. The stromal keratocytes also have a big role in glycolysis. Endothelium in fact is actually taking the glucose through the anaerobic pathway. Corneal transparency, we have already discussed the physical and physiological concepts behind it. We know the corneal epithelium and tear film's relationship. If the tear film is drying up, the cornea will lose its transparency. The arrangement of stromal lamellae has already been discussed. The two theories based on stromal lamellae arrangement is Maury's theory and Goldman's theory. And there is no corneal vessels, so it is the corneal avascularity which helps in maintenance of corneal transparency. The corneal dehydration is being maintained to 70%. And the certain factors which helps in the dehydration are the swelling pressures, the mechanical barrier that is formed by the epithelium, and the active pumping mechanism of the endothelium. The stromal swelling pressure is actually the keystone in maintaining the transparency of the corneal stroma, and the glycosaminoglycans are the mucopolysaccharides which are present, and the stromal swelling pressure is around 60 millimeters of mercury. There is a tight competition between the stromal swelling pressure and the intraocular pressure. So if the intraocular pressure is high and the stromal swelling pressure is less, there will be edema formed in the cornea because the aqueous there will be hydration of the stromal tissues. If it is the other way, let's say the IOP is too low, then also there is folding up of the cornea. So we should know about the stromal swelling pressure as the impenetrant pressure. Its significance is helping in the interfibrillary tension. It maintains the chloride channels. Also, the next role with regard to corneal transparency is the barrier functions that is formed between the epithelium and the endothelium. So now these are the pumps that are present in the endothelium. There is a sodium-potassium pump which is the most important pump. That is the sodium-potassium pump. Sodium is pumped here and potassium pumped out into the endothelium, and from the endothelium potassium is pumped out. Now few words about the applied anatomy of cornea is its optics are important with regard to microcornea, megalocornea, cornea plana, keratoconus, posterior keratoconus, sclerocornea,